Okay, we'll now talk briefly about sequence stratigraphic models for fluvial systems, having reviewed fascist models for some of the main types of fluvial reservoirs. So we saw this diagram before. I'm not going to go through it again, but again, just to remind you that sea level is not one of the controls listed here on river type. So we have to think a bit more broadly than the sequence stratigraphic models that we've used for shallow marine sections. However, let me just remind you of this diagram that we talked about again a couple of days ago. So this is a diagram showing a series of time steps from oldest at the bottom to youngest at the top, relating those to positions on a sea level curve, from falling sea level to low sea level to rising and high stand sea level. And we related that to the cutting and the filling of incised valleys. Now, the key thing here is these models, these apply to parts of rivers which are close to the shoreline, typically within a few tens of kilometers of the shoreline. Those are the parts of rivers where lowering of sea level does have an impact on how the river behaves, both cutting valleys and also filling of those valleys. And in places, direct evidence of marine influence in the form of tidal deposits and estuarine deposits infilling valleys cut by rivers. However, if we want to think about regions away from marine influence, we have to think a bit more broadly. So this top diagram is sort of a schematic cross section from a mountain belt through an alluvial and then a coastal plain. Then here we have the shoreline and then the shelf. So the valley fill models I just showed you would really relate to this part of the profile, and here close to the shoreline. Now, one thing that's shown here, and this is true in many sort of conceptual models for fluvial systems, for rivers, is that from the hinterland to the shoreline, we have a nice, smooth profile. Steep gradients in the mountains, in the hinterland, and that gradient gradually decreasing as we move towards the shoreline. And that smooth profile is referred to as the graded stream profile. And that's something which is shown in more detail down here at the bottom, this graded profile. That's a bit of an idealized profile. In reality, modern rivers don't show that nice smooth profile. But what we're trying to express here in this idea is that the gradient here, as it decreases, that means that the discharge, the amount of water which is flowing through the channel is small here, and it increases towards the right. That occurs because we have other channels, tributaries, feeding water into the main river channel. The amount of sediment that we're carrying basically decreases, so we store some of the coarse grain sediment in particular in these steeper parts of the profile, and the slope is obviously decreasing in that direction. So this is a bit of an idealized concept, but we can use it to think about how deposition might change if we change the position of that graded profile. Where might we get deposition? Where might we get erosion? And can we use that to think in sequence stratigraphic terms? The other thing about this idealized profile is, if this really is a graded or an equilibrium profile, any water or sediment we add at the top, it basically flows through the system and it exits at the bottom. Okay. So let's think. We can think about two different basic patterns in here. So these diagrams are showing again a cross section from a mountain belt down towards the basin on the right, and the equilibrium profile or the graded profile. Those are these these curved lines through here. So one thing that we can imagine doing is if we start off in this position in here, this is our graded profile, okay? If we then lower that graded profile, that gives us the potential to erode. A river which starts off in this position and is trying to reach this graded profile at the bottom, the way it can achieve that, it can reach that graded profile, is to erode. So this might be the case if we have tectonic uplift, for example. We start off with a channel like this, a graded profile like this. We then raise the land surface through tectonic uplift, and the river wants to cut down to reach back to its original position. The bottom image here shows the reverse. So here we start off with this graded profile down in here, and in this case, maybe thinking about tectonic subsidence, that that profile subsides and the river has to build upwards and deposit to reach back to its graded profile. So that means we're generating accommodation, and the river wants to fill that accommodation. So again, the text at the bottom really just repeats what I've just said. But thinking about how we change the position of that graded profile, that gives us a way of thinking about accommodation space. Okay, now let's think of a little bit more, let's still think of it again conceptually about how we might, other ways we might change that graded profile. Instead of shifting the whole profile up or down, we could also tilt that profile. So in this case, what we're showing is this is the original graded profile, but in this top image, we have tectonic subsidence which is greatest on the left, so that's greatest towards the basin margin, and the magnitude of tectonic subsidence, the size of these arrows, it gets smaller towards the right. So that indicates we have less subsidence on the right, more subsidence on the left. And if the river wants to, re-establish, keep up with that original graded profile, we have to have more deposition in here, because that's where we have more subsidence, and we have less deposition on the right where we have less subsidence. So this kind of subsidence pattern, greater subsidence towards the basin margin, that would be typical maybe in foreland basins, because this is where we have loading of a mountain belt that pushes down the land surface and creates more accommodation space. Okay, the bottom image shows the same kind of thing in reverse. Here we have our original graded profile, but if we have uplift in this case, which again isn't uniform laterally, greatest uplift towards the left, smallest amount of uplift towards the right, well then what that means is we have potential for more erosion on the left and less erosion, more erosion on the left in an up dip area, less erosion towards the right in a down dip area. So the key thing here is, we can also think about the effects of tilting. But again, the key thing here is we're really thinking about tectonic subsidence, not sea level. It's what happens due to tectonic subsidence or tectonic uplift as the driving mechanism here. Okay, so that maybe gives us an idea about how we can think about how accommodation varies, but of course we also have to fill that accommodation space, and that gives rise to patterns in the way that channels are stacked. And there's sort of two things we can think about here. So one is the aggradation rate. That's the degree to which the rivers are building up vertically, and that's really a function of the accommodation space. So if the rivers are building up slowly, in other words, we have a low but gradual increase in accommodation space, then that gives us, the river channels become densely stacked. We end up with multilateral and multi-story bodies which are well connected. If that aggradation is building up rapidly, that tends to mean that the channel bodies are less well stacked. There's a potential for them to be more isolated, and to be poorly connected with each other. The second thing which is important here is avulsion. Now, avulsion is a term which I don't think I've used. I'll explain in a couple of slides' time. Avulsion is the rate at which the channels switch position. Okay. If a channel switches position slowly, then that means that we have relatively few channel deposits, and they tend to be rather isolated and poorly stacked. If a channel switches position rapidly, then that gives us more channel belt deposits. It means they're likely to be better connected. We've already sort of discussed that actually in general, low rates of channel switching, that, or low mobility of channels, that might be meandering or anastomosing channels, for example. High rates of channel migration, that again is maybe more typical of braided rivers. The width to thickness ratio of individual sand bodies is also important, and we've also related that to different types of river channels as well. So let me show you some interpretations that maybe give you a way of approaching how you might interpret fluvial rocks. So here we've got a vertical succession, a schematic log through a series of channels, kind of stacked channel sand bodies separated by floodplain and lake deposits. So here we have intervals of where those fluvial sand bodies are well connected. They're densely stacked. They're amalgamated. These would represent periods of low accommodation. Then basically we have in here isolated channel bodies. We have some lake deposits represented by these limestones. This would represent a period of high accommodation generation, and therefore less well-stacked channel bodies. You can see towards the top of this interval, the channel bodies are becoming more closely stacked. So this corresponds to a change from high accommodation back to low accommodation. And in fact, in here we have, in this model, some prominent erosion surfaces. Those would be maybe periods of relative uplift. So removing accommodation, generating erosion. So we can think about explaining those patterns in the context of accommodation space. And there is this idea that, okay, these widespread erosion surfaces, these are effectively sequence boundaries in a non-marine setting. These densely stacked channels, those essentially would be the low stand systems tracts. These widely spaced channel bodies with lacustrine deposits preserved, those would be essentially the transgressive systems tracts. And then the high stand would be where we're seeing a change from poorly connected, widely spaced channels and an upward change into more closely connected, more densely stacked channels. Okay, I said a little bit about this term avulsion, so let me just sort of repeat that again. You've got a series of maps in here and a cross section at the bottom. The maps are maybe more informative in terms of explaining how rivers switch their position. So in A here we have a channel. It's slightly sinuous, and when that channel is in flood, we get a cutting of a crevasse channel, a small channel out of the main channel. It cuts through the levee, and then some of the sediment and water from the main channel is then fed out as a crevasse splay onto the floodplain. So this would be a typical scenario when a river is in flood. Now, that rivers don't just flood once, they flood repeatedly during times of high discharge, high volumes of water and sediment that they're transporting. So B in here shows the same river channel, but in this case, maybe after several tens of flood events. So here during flood number 20 or number 30, for example, that crevasse channel, it's used again, it's a weakness in the levee. So now the river is diverting a lot of water and sediment through that. And you can see it's basically built out really a very large crevasse splay. You know, it's been reused again and again in multiple floods. And you know, during the flood period itself, maybe most of the sediment and water now is now moving through this crevasse splay or network of crevasse channels, and relatively little is moving through the old channel. It becomes partly abandoned. And at some point, if that process repeats, when the river is out of flood, it just stays in this new position. It basically reuses and occupies maybe the largest of these crevasse channels, and that then becomes the new channel position. And the old channel position is now fully abandoned. Okay. And what you can see there is that the channel has now sort of switched position from here to here. And there's been a particular point where that jump has taken place. And that process is avulsion. That switching that's what we mean by avulsion. And we do see the effects of this in the rock record. So let me show you an example here. This is a cliff face about 200 meters in height. Photo of the cliff face there, and then a line drawing down below. And the sandstone units in the cliff face in here, those are channel bodies. They are channels which are somewhere between braided and meandering. And the finer grain material in between there are floodplain deposits. And what you can see is we see there are places where the channels are stacked vertically. They're also, laterally offset from each other. And we can trace out those individual channel bodies. We can see they're vertically stacked there, but they're not occurring within a valley. There's no sequence boundary, no big erosion surface containing these stacked channels. They're just switching position. And this sort of switching position is interpreted to be the effects of avulsion. So maybe the take home from this is that, trying to understand these concepts is not necessarily very straightforward. We do have sequence stratigraphic models that we can relate to changes in accommodation space. And largely there, we're thinking about tectonic subsidence as the driving mechanism. But we also recognize that this avulsion process, this is inherent within any river. It's part of how they operate. This can also give us these sort of clusters of sand bodies, which are harder to predict. We don't predict these in a sequence stratigraphic sense. Okay, other important things. Well, I mentioned paleosols a couple of times briefly, but paleosols are important because they tell us that we shut off deposition. If we form a soil, well, we basically have to give the plants time to grow roots, time. The soil is not just the plants, it's also some movement of minerals and clays within the soil. That takes time. So where we see a soil or a paleosol, that's an ancient soil, that tells us we have a pause in deposition. That's useful for us because that tells us there's time tied up in those surfaces, and potentially we can correlate them between sections. Some paleosols have a specific character, which again helps us to correlate them. So coals, for example, so those are very organic rich soils. They preserve lots of carbon. We need to have a high groundwater table, waterlogged conditions to keep that carbon reduced so it doesn't oxidize and then just disappear. So coals tell us, we have a break in sedimentation and also high groundwater. We can also get calcareous paleosols or calcretes. Those form when the groundwater is low, typically in arid or semi-arid dry climates. But again, they're also important as potential markers. And paleosols we can use to correlate, and changes in paleosol type also maybe tell us something about the water table conditions through time. So let me show you one model based on this. It's a variation of one we've already talked about. So here we're seeing low stand systems tract. There's a regional erosion surface. This is our sequence boundary. There's a valley in here associated with the low stand systems tract. And outside of the valley, we have paleosols, which represented by these vertical lines. And these would maybe be associated with periods of low groundwater. So these would be well-drained paleosols. Above that, we have the transgressive systems tract. So here, basically, we have channel or sand bodies which are not connected. They're not stacked. And particularly in the transgressive systems tract, we have these types of paleosols in here, marked by these upside down V shapes. Hydromorphic soil. Well, what does that mean? That means basically we're looking at a coal. It's a soil which records waterlogged conditions, high organic carbon preservation. So coals are typically associated with transgressive systems tracts in a non-marine setting. And then the high stand systems tract here associated again with poorly connected channel belts. They're becoming a bit better connected as we move upwards through the profile. And in here, you'll see we have a change from coals into other types of paleosol as we move up through the section. So again, paleosols are good markers of time. They're good correlation markers. And in some cases, we can also use the character of the paleosols to tell us something about how groundwater has changed through time. Okay, that's a good place to pause. We're going to move on to an exercise next.